an example of a use case integration. It will be the AI-based workflow for coding performance prediction. It is our application 5, which will be presented by Lisa Sahlmann from Helmholtz-Zentrum, Hereon. Lisa, please start. The floor is yours.
Okay. Thank you, Natalia. So, App 5 is basically an extension of App 3 that we heard earlier. So I'm going to give you a really short recap on what App 3 was about. So it already has been introduced by Nuran, and it's a finite element based simulations, and it simulates the inhibitor performance in a coating defect. We have passive and active protection here. Active protection means that through when the defect is in the coating, we get the active protection, and the passive protection means that we have this through the protective layer when there's no defect. Through the defect, the primer is exposed to the environment, and then pigment particles dissolve and can travel to the metal surface to provide the protection. So far, chromium-based coatings have often been used, but as we've already heard in this work, lithium coatings are tried out as active protective coatings. It is the App 3 model is focused on lithium carbonate, and it tried to model the process that occurs in the primer and on the metal surface. Primer and here the metal surface. There were two types of experiments conducted. The first one was leaching curves, which were conducted by Nobel, and potentiodynamic polarization measurements done at TU Delft. The thing about the finite elements models, as we've already seen before, is they have high model complexity, but the computation time can, depending on the geometrical setup, take quite long. So our idea was that we could instead train a machine learning model which makes faster predictions and utilizes a database generated by the finite element model. So how did we set up this training data set? We have run App 3 for 270 different cases to generate the database. So you can see the different parameters here. We have the pigment volume concentration, the defect width, the primer thickness, the water layer thickness, and the defect depth. And then we took different numbers for these parameters. And it might sound a little counterintuitive to first let the App 3 run for 270 cases. It takes a lot of time to generate them and then train a machine learning model. But the big advantage is that once you've trained the machine learning model, the prediction goes within seconds. And the outputs of the machine learning model are then simulated at 2 hours of simulation time, which equals 2 hours of leaching time. The output is extracted here at the bottom of the surface at the electrode, and the output parameters are the inhibitor concentration and the current density. And as I mentioned, it reduces the computation time because you can just put in these 5 parameters, and then you just with a click get the prediction for this special geometrical setup that you want to know about. Some insights into how well the machine learning model performs. So we were mainly using random forest-based models. So a random forest and an XGBoost. We have the random forest in blue here and the XGBoost in orange. Instead of using the whole data set for the training, we started off with 10% of the training data, and then we increased the amount of data in each training round to see if the performance of the machine learning models improves when we add more data. And in each round, we did a cross-validation, which means in every round, the dataset is again divided into 6 subsets, and then 5 of them are used for training, and 1 is used for testing. So to get a good view on how the machine learning model is performing on unseen data. And this cross-validation thing is done in 6 rounds, so every round switching the test set. And in this way, the performance and especially the generalizability of the machine learning model can be validated. And what we can see is if we only train for 10% of the training data, so 27 cases, the performance is not good at all. But then if we increase the amount of training data, we see that the R-squared goes up until 0.8, which is already quite good. And we see the same trend when we look at the normalized root mean square error. Increasing the number of data points leads to a decrease of the error. And now I want to take a closer look at this case where we trained on all the training data that we had. So I plot the different targets, the inhibitor concentration and the current density with their minimum and maximum. These are the 4 different targets that we used for the model, and we have the training data set in blue and the test data set in orange. So this is one fold of this 6-fold cross-validation, and we can see that for the inhibitor concentration, both training and test set perform really well. The prediction is really close to the perfect correlation line, and for the current density, we can see that the prediction is still pretty good, but it is a little more scattered than for the inhibitor concentration. We don't know yet why this is the case, but the overall performance is still really good. We get an R-squared of 0.0. Oh, I mixed the R-squared and the root mean square up here. The root mean square was 0.02. When we look at the XGBoost, we can see something really similar. The prediction for the current density is a little more scattered, but in general, we get a really good prediction with an R-squared of 0.87. And now that we've seen the machine learning models, how they perform, the question is how can we actually use the App5 to design a coating? So we can use App5, the machine learning model, to predict the inhibitor concentration and the current density, as we saw in the previous slides, for example, for different pigment volume concentrations. Here I use a primer thickness of 14 micrometers, and the other inputs are these here on the right side, and then I did the same for other primer thicknesses. And so I used 14, 24, and 40 to see the differences between them. And this is basically how we can use App5 for coating optimization. We test different scenarios, and then really depending on your coating that you want to have, you can decide what is the optimal coating for you, which performance you want to have, and so on. And here, it's just a little more insight into the machine learning model, the feature importance. So we got the pigment volume concentration as the most important input parameter. This might be because the leaching behavior from the primer changes significantly across the different pigment volume concentrations. And that comes from the percolation model, which was already explained earlier by Nuran. And the second most important input parameter is the water layer thickness, probably because it influences the replacement of depleted oxygen near the electrode. So to conclude, the App 5 relies on an extensive database which has been generated using the App 3 model, the finite element model. And the machine learning models, the random forest and XGBoost, have been trained on this database, and they show really good performance in predicting the current density and the inhibitor concentration. And the big advantage of App 5 is that we can use it for fast predictions, and we can use it to optimize coatings. And now I also want to go in the platform here to show you how you can run App 5. Okay, I hope you can see the screen again. So again, I'm on the landing page, and here we have the projects, and I'm part of this demonstration project. And when I go in here, I can see the workflows. There are different ones, and one of them is the App 5 workflow, which when I click here, I can get a preview of the BPMN, and I can also start it here. And once I started it, I can go down and I see that I started it here and it's in progress. When I click on the logs, we can see, okay, it has been started. And now I can put in some numbers. So let's try this one out. And now I click on complete. And when we look at the logs, it's still the same. Maybe I have to. Okay, it's still in progress. So usually you get the results here at some point. Maybe we have an example here. Yeah, here it's a completed one. So when I look at the history, we can see the predictions for the inhibitor concentration and the current density. And since I ran the cross-validation, we can also get a standard deviation across the different models for the prediction. So how sure is the model about its predictions? Yeah, and that's basically how you can use the App 5.
Thank you very much, Lisa.